Okay, Math 153 students, in this section 13-1, we're going to talk about evaluating definite integrals. Now, in all the Riemann sum exercises that we did in 12-1, we were calculating approximations to definite integrals. So a definite integral has values a and b, and that's what distinguishes it from an indefinite integral. And if we go back for a second to the Riemann sum problems that we did, like this one, given the graph of a function below, use a right Riemann sum with three rectangles to approximate the integral from 3 to 6 of f of x dx. So in all these exercises, that was what we were doing, was approximating definite integrals by using Riemann sums. And every single time down at the bottom, we wrote a statement like this. Found the number 27 by the process, and then our conclusion was the integral from 3 to 6 of f of x dx is approximately equal to 27. That's approximate and not exact. The approximation would be better if we used more rectangles, and increasingly so. The more rectangles we use, the closer the approximation to the exact value of that definite integral. So for example, in this problem we used 3 rectangles. We could redo this, subdividing each of those in half using 6 like that. Then we could divide each of those intervals in half and use more and more. Every time we created this finer and finer subdivision down here, we would be using more rectangles, and the approximation that we would achieve would be more and more accurate to the value of the definite integral. So again, with the Riemann sum calculation, what we're doing is approximating a definite integral. Okay? And the more rectangles that we use, the better the approximation. And the way that we express that is this statement right here, which is the integral from a to b of f of x dx. This is actually the definition of what a definite integral is equal to. See the contrast there? It's approximately equal to versus actually equal to the limit as n goes to infinity. And n is the number of rectangles. So up here, there's no limit, and that's approximately equal to. Down here, the limit as n goes to infinity is exactly equal to the definite integral. That limit is really generally, depends on the function involved, quite hard to compute directly. But we can avoid doing that because there is this big theorem, very important theorem in math about the definite integral and how to calculate its value exactly so it's equal to that, avoiding calculating this hard to do limit. Okay, and so the next rest of this page and the next page are about using this formula to evaluate definite integrals. Okay, the integral from a to b of f of x dx is equal to capital F of b minus capital F of a. B is the number on top of the integration sign, the elongated S symbol, always. And A is the number on the bottom. And in order to use this formula, you need to know what capital F is. And this is what it is. Capital F of x is an antiderivative of f of x. So this formula in the box shows the connection between the definite integral, which is a number that we would get I just go back here to the definite integral is the number that we would get by increasing the number of rectangles here, taking the limit as n goes to infinity, and figuring out what that limit would be equal to. We didn't use too many rectangles here. We used 3. We got 27 for approximately the integral. If we used 6 rectangles, the approximation would be better. Then we used 12, then we used 24. We can continually increase the number of rectangles get a better and better approximation to the definite integral. The exact value of the definite integral is the limit is also equal to this difference, where we use the antiderivative or the indefinite integral to calculate this difference. We plug the numbers b and a into the antiderivative, and that's how we can evaluate the definite integral without directly calculating the limit, which is a big, huge labor-saving thing. And it also is the connection between a definite integral and an antiderivative or an indefinite integral. And that's why the notation that's used is similar for both of them. But the definite integral has a and b, the indefinite does not. You're going to see that in all these examples coming too. Okay. So I'll dive into this example. F of x equals x squared, and a equals 1 and b equals 4. And part A is actually what we did in the previous set of notes. The thing I keep going back to with the rectangles. So we're going to do that once again here in part A. I'm going to draw a picture here. So we got our friend x squared as a function. We're going from 1 to 4. So put 1, 2, 3, 4. X squared is pretty easy to work with. We're going to have this point right here would be 4 comma 16 0 0, and if I make axes like that, and then I'll have a 1 1. It's going to be a little bit approximate, but good enough. And 2 4. And 3 9. Sorry, my points labeled there a little bit off where they are, but you get the idea. That of course keeps going, and that's our friendly neighborhood parabola x squared that we know and love. Now for our rectangles, we're supposed to do a left Riemann sum, so we're going to use rectangles like this one, and this one, and this one, and that's it for our left Riemann sum rectangles, R1, R2, and R3. And you can make a little rough table like the ones we were using before. R1, R2, R3. We have a width of the rectangle, we have a length, and then we have the area of the rectangle, which is the width times the length. All three of these rectangles have width 1 because we're going from 1 to 4 on the x-axis, divided up into 3 equal parts. So 1, 1, 1. And the length is the height, so there we have to think a little bit. R1 has the point 1, 1, so the y value there is 1. So this is a height of 1. R2 is a y value, this here is the x value 2, so the y value of this point is 4, so that's here. R3 uses this point right here, and on the graph it's this point right here, x value of 3, and the y value is 9, so the value 9 is the height of the rectangle or the length of the rectangle. Then we multiply, multiplying by 1, so easy. And then we get this. And then we're doing the sum down here, so I'll just put that down here. This is the 9 plus 4, 13. This is 14. And that's the integral from 1 to 4 of x squared dx is approximately equal to 14. That's the conclusion of that. And if we did it again with 6 rectangles, it would still be approximately equal to, but it would be a better approximation, less error. Okay. Now we're going to calculate not approximately what it is, but exactly what that value is. We can see how close 14 actually is. But this is a totally different way now. This would be very hard to do with the limit of rectangle areas, but we can do it with antiderivatives without too much trouble. Two-step process. Step one goes back now. This is where they connect up these two concepts. Find an antiderivative f of x. So this is the indefinite integral. So look carefully at this. I am not writing the limits, or the values a and b. We call those limits of integration. I try to avoid that word here because of the word limit that we have had way back at the beginning, and right here we're talking limits. So I don't really like to say limits of integration, but that is what a and b are called. Now, however, in the antiderivative, there are no a and b. So that means the 1/3 x to the third. Now, if we're finding the general antiderivative, we have to put plus c there. But when we're using an antiderivative to calculate a definite integral, meaning when we're using this formula in the box, we don't have to include the c. Okay. In fact, you make a tiny bit extra work for yourself if you do. So sometimes you do, sometimes you don't. If it says the general antiderivative, the part plus c is part of it. If you're doing it in this step one of these guys, you don't need it. So that's the function capital F of x. And it's going to be real important because in this formula up here, that's what we plug b and a into. So here comes the magic, right? So capital F of 4 minus capital F of 1, and that's equal to 1/3 times 4 to the third minus 1/3 times 1 to the third. And where that's coming from is plugging the b and the a into the antiderivative that we got in step one here, and subtracting. Always capital F of b, the top number, minus capital F of a, the bottom number. I don't know what this is, and I don't have a calculator right now, so let's see if I can do this. 64/3 minus 1/3. Yeah, we can do this, right? 4 to the third is 16 times 4 to 64/3 minus 1/3, common denominator, which is good. 64 minus 1, 63/3. 60 divided by 3 would be 20. So 63 divided by 3 would be 21. So I'll run out of the box here, but it's okay. I'm going to just put it down below here. Kind of contrast with this up here. 14 is approximately the answer to the definite integral. Now we know the integral from 1 to 4 of x squared dx is exactly equal to 21. So now that we got some numbers we can talk about, you can make a little bit more sense in one's brain about the more and more rectangles bit. We did 3 rectangles up here, very small number of rectangles. If we did the same type of process, but we used 6 rectangles, so if we divided each of these again and created more rectangles, we would get a number that would be closer to 21. 14 is pretty far. If we used 100 rectangles, or a big huge chart. Really cumbersome to do that, but you could do it in a spreadsheet actually. These charts here lend themselves to that. You could do it. Your value of your sum of your areas of the rectangles, there would be many rectangles in there. It would be close to 21. Okay, and the more rectangles you use, the closer it would get. And that's what we mean up here, that the value a definite integral is the limit of the Riemann sum. sums at n goes to infinity. And the theorem in the box gives us a way to actually calculate that using the antiderivative instead of directly using a limit, which is a huge advantage mathematically.